Right, so welcome everyone to this week's Western Hemisphere Colloquium on Geometry and Physics. Before we start with the talk, just want to go over the general format. During the lecture, all participants are going to be muted. If you'd like to ask a question, please send it to everyone in the Zoom chat. And either the speaker will pick it up, or will aggregate questions from the chat and communicate them to the speaker at various points during the talk. At the end of the talk, we will have a Q&A session. And there, if you'd like to ask a question, please use the raise hand feature in Zoom, and we will call on questions in order. Okay. Having said that, let me happily introduce you to today's speaker, Davide Gaiotto, from the Perimeter Institute. Davide will be talking about integrable Kondo problems and affine geometric Langlands. Davide, you want to share your screen again?
Hello, yes, and let me just share the slides.
Fantastic, and give me a second
will also
to mute everyone and then unmute you.
Upload slides to the chat. Sorry.
Okay, good. Welcome back.
Even ask me. Good. Okay, I think everything is done aside.
Yes, and also, so if you've been paying attention to the chats, Davide's slides are there to be downloaded if anyone would like to do that. Thank you, and please go ahead.
Okay, so I'm going to discuss work done in collaboration with Kevin Costello, Jion Lee, Benoit Vichedo, and Jingxiang Wu. Lee and Wu are my PhD students at PI. It's a work that started by looking at some other physical problems in integrability and in two-dimensional conformal field theory, called Kondo problems. But soon we started wandering into a pretty complicated tangle of somewhat refined mathematical topics. And I've given a couple of talks until now, which start from Kondo problems and move into these mathematical topics. But today I will try to find a different route, where I start from the gauge beta correspondence by Negrov and Shatasvili and its affine generalization. The main message that I want to bring you today is that a certain topic in integrability called the IMOD correspondence is secretly related to an affine generalization of the geometric Langlands program, and physically also within string theory to the problem of studying S-duality of the three branes in the presence of a transverse sarcomere. Now, a lot of the topics that are sketched on this slide and their connections have been developed by other researchers. And I will not even try to give a proper referencing during the talk. I will leave the references for the papers when they come out. So I hope I will make it clear if there is something that I hope it's particularly original, but otherwise feel free to assume that a lot of this has been done by others. And I hope that the corresponding authors will not feel offended by this approach. So let me start from the beta gauge correspondence. This is a peculiar relationship between supersymmetric gauge theories and spin chains, integrable systems, integrable spin chains. It starts from the observation that the same set of equations, polynomial equations, control two things. They control the supersymmetric vacua of gauge theories with A supercharges, but also there are debate equations for some spin chains. So more precisely, one is looking at gauge theories with A supercharges whose gauge group and matter content are described by quiver in the shape of an ADE linking diagram. The simplest example you should keep in mind is just the supersymmetric version of QCD. We have some UN gauge group with M flavors. You're taking a gauge theory which could be two-dimensional, three-dimensional, or four-dimensional. You're somehow compactifying it down to two dimensions, turning on a supersymmetry breaking parameter, a half EPS supersymmetry breaking parameter, and looking at the vacua of the system. These vacua are described by some twisted chiral ring relations, which are polynomial in form, and well, unless you're working with in four dimensions. And as I was saying, these are debate equations for some spin chain. Throughout this talk, and in general, I particularly like the three-dimensional case where you study a 3D unequal form theory compactified on a circle. And in that case, you find a relationship to debate equations for an XXY or XXZ type spin chain, which is a spin chain where the individual sites carry representations of the quantum group. And this data is used to build up commuting Hamiltonians, commuting conserved charges. It's a peculiar correspondence in many ways. For example, a given spin chain is not mapped to a specific gauge theory, but rather a collection of gauge theories with all sorts of ranks. For example, if you study these sort of QCD-like theories, you let the rank vary from 0 to M, and that allows you to cover all the states of a SL2 spin chain with fundamental representations at each site. One of the reasons I like the three-dimensional version of this story is because the three-dimensional gauge theories enjoy mirror symmetry, which has some interesting consequences at the level of the spin chains. Now, this correspondence has given rise to a lot of mathematical work, which has demonstrated clearly that indeed the twisted chiral ring and the quantum cohomology or quantum K-theory of these gauge theories carry representations of these quantum groups and is in correspondence with these spin chains. And a lot of work to find dark matrices, in particular, out of these gauge theories. But I think it's fair to say that physical explanations of this phenomenon tend to be a little bit complicated. The simplest I know involves a rather long duality chain identified by, I think, by Costello and Yagi, which connects these 3D gauge theories all the way to, or 2D gauge theories, all the way to a four-dimensional Chern-Simons setup. I mention it just because four-dimensional Chern-Simons theory will play a role in the rest of the talk, but not through this duality chain. So if you are familiar with the work by Costello and Yagi, please do not confuse it with the appearance of Chern-Simons later in the talk. Now, my way into this topic was that the beta equations for the spin chain have an interesting scaling limit, which reduces the spin chain to the Godin model and makes contact with the Geometric Langlands program. I will discuss it in a few slides. Are there any questions?
Not yet.
Okay, very good. So I'm interested in an affine generalization of the gauge beta correspondence, where instead of considering a quiver in the shape of an ADE linking diagram, you consider a quiver in the shape of an affine ADE linking diagram. So the simplest example would be an ADHN type quiver, where I have a UN gauge group with M flavors, but also an adjoint hypermultiplet. Or more complicated quivers, such as a necklace quiver, with say 2 nodes and some number of flavors attached to each node. the expectation is that the supersymmetric vacuum of these affine quiver gauge theories and the corresponding twisted Cartesian relations should coincide with the Bethe equations for some quantum toroidal algebras. Now, Bethe equation, for some spin chain based on quantum toroidal algebras. Or more precisely, there is a slight difference between the A-type and D and E-type quivers, because the A-type quivers have an extra mass parameter. So depending on what I'm talking about, I should say quantum toroidal algebras or just affine quantum groups, but I'll come back to that later. Anyway, these quantum toroidal spin chains and their Bethe equations were only recently introduced, and I have not noticed yet an identification between the Bethe equations and the supersymmetric vacuum of the affine ADE type quivers. But it might be possible that might very well be possible this was noticed before. I mean, once you see the equations, it's quite obvious. This correspondence, if true, presumably has some string theory explanation analogous to the Costello and Yagi analysis that lands you on five-dimensional Chern-Simons theory. Indeed, the reason I've been interested in quantum toroidal algebras is precisely because they control the behavior of what's something called twisted theory or five-dimensional Chern-Simons theory. But also for today is because there is a certain scaling limit to these Bethe equations, which give you the Bethe equations of something called the affine Godin model, which is going to be the main actor of this talk. But it's somewhat difficult to directly introduce, and so obtaining it as a scaling limit is somewhat natural. Okay, still no questions? Okay. Now let me review briefly the dictionary of the gauge Bethe correspondence. So as I said, the shape of the quiver, the linking diagram the quiver is modeled on, tells you which quantum group controls the spin chain. So it determines the algebra inside the quantum that is defining the quantum group. The ranks of the gauge group controls the weight of the state in the spin chain. The number and locations of the fundamental flavors in the quiver control which representations you have at each side of the spin chain. And their masses control the sort of something called impurity parameter at each side. The spin chain is a closed loop of spins, and the boundary conditions around the loop are controlled by the phi parameters of the gauge theory. And finally, something called n equal to star mass, which breaks after the supersymmetry, maps to the Q parameter of the quantum group. And I mentioned I like mirror symmetry and the effect of mirror symmetry on this gauge Bethe correspondence. And on the other side, on the spin chain side, it gives rise to a strange bispectral duality, which relates the spectrum of spin chains with different numbers of sides and different gauge group, a different underlying group. I will not write down the Bethe equations. If you know them, and you know what I'm talking about. If you don't know them, they would look too obscure to be usefully written down on the slide. I will write down the scaling limit to Godin later on. But essentially, they look like products of a bunch of rational functions equal to 1. Now, the affine version of the story should have pretty much the same dictionary. The shape for the A-type, you will have an affine AN quiver, which is an necklace quiver with n+1 nodes. And the spin chain should be based on something called the quantum toroidal algebra, which is a two-parameter deformation of a universal opening algebra of a Kac-Moody algebra. I put 3 parameters here, Q1, Q2, and Q3, but just a convention. The product is set to 1. So this is a two-parameter deformation. Again, the position of the flavors in the chain and should control which representations of this quantum toroidal algebra you put at each side of the chain. These representations are not finite dimensional anymore. You should think about them as deformations of Weyl modules for the Moody algebra. Again, mass parameters and phi parameters enter in a familiar way. And as I mentioned, the A-type affine quivers have an extra mass, which acts on by fundamental hypermultiplets only on the links of this necklace. And this together with n equal to star mass gives you these two deformation parameters, Q1 and Q2. And again, there is mirror symmetry for this necklace quivers, which maps to a conjectural bispectral duality on the toroidal spin chain side. If you're looking at a quiver of type D or E, or if you turn off this extra bifundamental mass, the Bethe equations simplify a bit. They have fewer solutions, and the whole spin chain seems to be based on the quantum group for the affine Lie algebra, so the affine quantum group. I think there is a question. Is it for me?
It is for you, from Greg.
Yes.
Are matrix product states useful when working with these spin chains with infinite dimensional representations?
I'm not sure. The Bethe, as far as I know, the Bethe, so these spin chains have a Bethe solution. They're solved by some Bethe equations. As far as I know, the Bethe equation is derived in the standard way, where you just have some lowest weight states, and then you start building on top of them with some of diagonal elements of the transfer matrix, and then requiring periodicity these are the Bethe equations. But I'm a little bit, I mean, I've not looked at the details very carefully. Yeah, I will discuss. I do not know, a very good physical setup to encounter these quantum toroidal spin chains. With site, I really mean a site. So a spin chain is what is a spin chain? It's a system where I have a Hilbert space, which is a tensor product of representations of my quantum toroidal algebra or quantum group or whatever. And then out of the action of this quantum group or quantum toroidal algebra, with the help of an R matrix, I build some commuting Hamiltonians, some collection of commuting observables. So in any case, roughly speaking, I'll say yes. So again, I'm interested in particular in a certain scaling limit of these spin chains. The scaling limit essentially removes the deformation parameters. In the case of the Godin model, sorry, here, it simplifies the quantum group down to the actual Lie algebra. And in the case of in this case of the affine XXX spin chain, XXY spin chain, it simplifies down to an affine Godin model, which is just modeled on the Moody algebra. At the level of the Bethe equations, the simplification is quite easy to describe. The Bethe equations tells you that some product of certain rational functions is 1, and you're taking a scaling limit where this rational function look like 1 plus something. And so you end up with Bethe equations where the sum of some rational expressions equal to 1. So as far as I know, let me answer the question from Sasha. As far as I know, you don't have a quantum toroidal algebra based on D and E. But indeed, there is the quantum group based on the Moody algebra. Concretely, what happens is that when you look at these quivers, see, let me look at the ADHN quivers for simplicity. There is a global symmetry that rotates the joint. and it's not, it's distinct from the gauge, from the action of the gauge group on the joint. If I look at the necklace quiver, there is a global symmetry that rotates all the bifundamentals in the same, with the same charge. This gives some extra parameter in the Bethe equations. If you look at well, I've not drawn in my slides a quiver of D type, but if you look at a quiver of D type, you'll realize that all the UN actions on hypermultiplet, on bifundamental hypermultiplets are actually part of the gauge group. And so you don't get an extra mass parameter. Okay. So let me give a quick refresher of what the Godin model looks like and why is it related to the Geometric Langlands program. So the Godin model is an integrable system where the Hilbert space is a tensor product of finite dimensional or possibly even infinite dimensional representations of a Lie algebra. So you essentially take multiple copies of a Lie algebra and you try to build commuting Hamiltonians out of them. And there is this very nice collection of commuting Hamiltonians where you just take products, the inner product of generators from two copies of the Moody algebra, of the Lie algebra, finite dimensional Lie algebra, say ji.jj, divided by the difference of some complex numbers labeling the the spectral parameters or the impurity parameters or the size of the spin chain, and adding up over J. So it's a fact that these HI Hamiltonians commute with each other. You can recover them as classical limits of the XX of the spin chain transfer matrices. And you can also write down higher Hamiltonians, which are cubic or higher polynomials in the generators, but they're more complicated to write down. So it's a fact that these Hamiltonians can be diagonalized by a Bethe ansatz, which gives rise to some Bethe equations. For example, if you're looking at SL2 Godin model, the Bethe equations look like this. The Zi's are these parameters in Hamiltonians, the W's are the Bethe roots, the Ki's are essentially the spins, if you want the dimension -1 of the representations for each copy of the SU. And you want this rational expression to vanish. So you get a bunch of solutions for the WAs, for the Bethe roots. And if you just count the number of solutions for every choice of the KIs, you see that you're building up indeed enough solutions as to represent all the states in a tensor product of finite dimensional representations of SL2. The reason the Godin model gets tied up with the Geometric Langlands program is that these Hamiltonians and this integrable system appears when you study the conformal blocks of Kac-Moody at critical level. In gauge theory, it comes up when you study the ground states of a collection of boundary Wilson lines sitting on a Neumann boundary condition in n equal 4 super Mills. Now, if you don't want to forget about the Bethe gauge correspondence, you can ask what happens to the gauge theory as I do this limit for the spin chain. Right? You can ask what's the Bethe gauge correspondence for this Godin model. And if you think about the spin chain as having to do, the 3D gauge theory as having to do with the 3 branes ending on an S5 branes, then the scaling limit sends the 3 branes to the 2 branes and then to M2 branes. And so you could argue that this Godin model controls the vacua, the supersymmetric vacua of 2D defects in a 6D CFT. So it has to do with M2 branes ending on M5 branes. And this perspective was very useful in some work I did with Ed Witten on knot invariants. So you get connection to 24 super meals. Now, the affine Kondo model is not as easy to describe in terms of commuting Hamiltonians. Indeed, it's supposed to be something built in a similar way, where you have multiple copies of a Kac-Moody algebra acting on a tensor product of representations. You're trying to build some commuting objects in there. Writing down local Hamiltonians is messy, difficult. On the other hand, there is a rather clear proposal for building transfer matrices, commuting transfer matrices for this spin chain, which are sort of commuting extended operators. Classically, you build the Lax matrix, which is just linear combination of the Kac-Moody currents with certain coefficients. And then you compute the holonomy of this Lax matrix, the path order exponential of this combination of the currents acting on an auxiliary representation. So you take the Kac-Moody currents, you contract them with some SU2 generators acting on some auxiliary representation R, and you do this path order exponential, you take the trace over R, you end up with some complicated expression in the currents. And these expressions are supposed to commute for different values of the spectral parameter Z. Now, there are all sorts of challenges in defining this properly, because these are now really Kac-Moody currents, depending on some, physically they're like current, two-dimensional currents in a two-dimensional CFT, and we're trying to path order exponentiate them along some circle in my CFT. And there are OPE singularities when these currents come together. So this expression is badly divergent written as it is. It requires a proper normalization. So to discuss this expression momentarily, we'll have to start doing physics. But for now, let me just ignore those issues and just say that there is some kind of affine Kondo model which is defined by these transfer matrices. I find it fascinating that somehow this is supposed to come from a scaling limit of these quantum toroidal spin chains, where there didn't seem to be any troublesome renormalization to do. But that's something I would like to understand better. In any case, there is a conjectural collection of beta equations which are supposed to solve this affine Kondo model. I will discuss them momentarily. I just want to stress that the very reason people started looking at quantum toroidal algebra spin chains and their beta equations was to find a justification for these equations. In a sense, here is a situation where you kind of you get your beta equations even before you understand which integrable model they are about. Therefore, so the beta equations look very similar to the one for the finite case. For example, for the affine SL2, I'm writing them here. Essentially, they are modeled on the Cartan matrix for affine SL2 instead of being modeled on the one for finite SL2. And if you just start solving these beta equations in simple examples and counting the number of solutions, you see that slowly you're building up something that looks like a tensor product of wild modules for a Kac-Moody algebra. There are various parameters here you can play with. For example, these Ki integers control the spin of this wild, which representations are these wild modules. The sum of this K plus K prime controls the levels of the Kac-Moody currents, and so on and so forth. Okay, so if I go there. Okay, so let's just say there are these beta equations. They are conjecturally associated to this affine Kondo model. They can be obtained from a scaling limit of the quantum toroidal algebra. So they seem to make sense. And now you might start wondering if there is some kind of a analog to this, to all of this story about Kac-Moody algebras and geometric Langlands and so on and so forth. Now, for the finite Godin model, the relation to the geometric Langlands program becomes particularly clear through the correspondence between the affine Godin model and operas. So I mentioned quickly that the Godin model, so not affine, the Godin model and operas. I mentioned quickly that the Godin model and its Hamiltonians have to do with states for boundary Wilson lines in a normal boundary condition in N=4 super Mills. If you apply S-duality, these become boundary Tooth lines at some boundary condition called an unpoled boundary condition. And if you ask yourself what are the states, what are the ground states of such a system, you encounter the notion of operas. Or alternatively, it's a celebrated result in geometric Langlands that the beta equations for the Godin model also solve a different problem, which is to produce something called operas with trivial monodromy. Now, I'm not going to describe what an opera is in general. Let me just remind you of what an opera is for SL2 gauge theory. So an opera in SL2 is just a Schrödinger operator, equipped with a certain natural rule for changing coordinates in different patches of some surface. Essentially, the condition is just that the Wronskian would remain well-defined in different patches. The operas with trivial monodromy are Schrödinger operators which have regular singularities at a collection of points Zi, which are the same Zi that appeared in the beta equations. These regular singularities have coefficients such that the monodromy of the Schrödinger equation around these singularities is potentially logarithmic. So if you try to solve this equation near Zi, you find a solution which goes like Zi to the k over 2. In another solution, it goes like Zi to the minus, so one was minus k over 2, the other was k plus k over 2 plus 1, anyway. But the one that goes like z to the minus k over 2, at some point in the Taylor expansion has a logarithm. So that the Schrödinger equation have logarithmic singularities, logarithmic monodromies. So an opera is said to have trivial monodromy if the residue at these poles have been adjusted carefully so that the monodromy is not logarithmic, but it's trivial. So if you look at what conditions are required for this to happen, you get some very complicated polynomial equations in the CI. But it turns out these polynomial equations can be recast as in the same form as the beta equations for the Godin model. Okay, so I see a bunch of questions. Perhaps I can try to answer some of them.
So a few are from quite a few slides back.
Yes. So the scaling limit to the Godin model is definitely related to his equations and conformal blocks. Indeed, this Schrödinger equation I'm writing here is just the classical limit of a BPZ equation. Now, for the functional beta and sats for the affine Godin model, maybe I'm not sure. I'm not very familiar with the actual details of the beta and sats solution of the quantum toroidal spin chain. Now, one interesting feature of these beta equations, is that in the gauge theory setup, you could understand them by going to the Coulomb branch of 4D gauge theories. not the Foddy gauge theory. And then you would have a collection of boundary monopoles and a collection of smooth monopoles in the bulk, which are attracted to these boundary monopoles. And these Bethe equations were sort of the electrostatic condition for these smooth monopoles to be balanced between all of these Dirac monopoles placed at the boundary, very roughly. The reason I mention it is because when you then look at these Bethe equations, the affine Bethe equations, you can wonder if there is any way to get a similar interpretation. And I think you can, if you think about N=4 super Mills in terms of D3 branes, and the Coulomb branches, separating the D3 branes, the smooth monopoles are the one string stretched between the D3 branes. Now, if you stare at these Bethe equations for a while, you get the impression that now there are the one string segments stretched between the D3 branes in one direction, but also around. So I think you can interpret these affine Bethe equations in terms of a collection of D3 branes in the presence of a transverse circle with some dynamical D1 branes that connect them from in one direction or in the other. Alternatively, right, so if there is a geometric Langlands interpretation for these Bethe equations, for the affine Kondo models, it probably has something to do with D3 branes in the presence of a transverse circle. I can say more about that. For now, let me just discuss the relation between a affine Kondo model and opers. Yes. Although they cannot be realized as semi-infinite D1 branes now. So one would need some other type of brane which is a magnetic source. I'm still trying to figure out the correct brane setup. But yes, if you look at the Bethe equations, there are both fixed sources, the Zi's, which are the position of whatever Dirac-like singularities, and then these W's and W primes, which are positions of these conjectural monopoles. So I think it does not make sense quite in gauge theory, but more in some kind of a little string theory. So N=4 super Mills is engineered naturally by compactifying the 6D CFT on a torus. Now the 6D CFT has an ancestor which is a 6D little string theory, which is an extra mass scale and describes M5 branes in the presence of a transverse circle. So if you compactify this little string theory in a torus, you're going to get a four-dimensional theory, which I'm not sure is a quantum field theory, but it resembles an N=4 super Mills, except that it has extramagnetically and electrically charged particles, which arise from the D1 branes or F1 strings going around the circle. I think the theory and its S-duality properties are what underlies affine versions of geometric Langlands. But the only evidence I have is that these affine Bethe equations seem to have a reasonable interpretation in terms of moving to the Coulomb branch in a manner analogous to the paper with Witten. Okay, so a nice result is that the same Bethe equations which solve the affine Kondo model also have an interpretation in terms of opers. Let me just again restrict to SL2. These opers are quite more interesting than the ones we were considering before. The one for the finite Godin model have trivial monodromy, literally. We engineer them so that they have trivial monodromy. So they have no interesting transport coefficients. The only interesting property of this opera is what's the actual residue that you find here. And this matches the value of some Godin Hamiltonians. But in the fine Godin model, you encounter operas which have more structure. They're called sometimes affine operas in the literature, although they can really be treated as standard operas, except that they depend on a parameter. They're Schrödinger operators which depend on an explicit h-bar parameter. So they have an actual interesting potential. This sort of exponential times a polynomial. On top of this potential, they have a bunch of quantum singularities, sort of quantum corrections, which don't go like 1 over h bar squared, but just order 1, and which introduce extra regular singular points. And the requirement is that you want these extra quantum singularities not to add monodromy. So you want this Schrödinger equation to have no extra monodromy around these quantum singularities for any value of h bar. So it's a much stronger condition than before. We have a family of opera, a pencil of operas, or an h bar opera, and you're adding singularities that have to have trivial monodromy for all values of h bar. And if you try to write down constraints for that to be true, it looks, at first sight, it looks impossible. Okay, there is one question by Greg. I can try to discuss the Hitchin system perhaps in a little bit, because I'm really curious about the answer to your question, but I have not found a good answer for now. So it's really important that we are not just looking at the Oper it's sort of alternatives to the Oper manifold, but there is this spectral parameter, this h bar. But it's possible to show that you can solve this problem if you have a solution of these equations. The remarkable fact is that now the very position of some of the singularities becomes a parameter in the beta equations. So in the standard setup, you pick the position of your singularities, and then you adjust the residues. In this setup, you pick your potential, which tells you where the zi's are. You can put extra singularities at the locations of the zeros, and you can put even more singularities away from the zeros, but only at locations which are determined by the beta equations. Okay, so this is sort of the more mathematical circle of idea. There is an affine analog of the relation between Godin model and operas. It involves this affine Godin model with this peculiar affine style collection of beta equations, and it involves this rich variant of operas with trivial monodromy. I should stress that these operas have an interesting potential, so they have interesting transport data. You can look at solutions which go to 0 at infinity in various directions and compute Stokes matrices or whatnot. These Stokes matrices and this transport data are going to match in interesting and rich ways the transfer matrices of the affine Godin model. Now, if you've seen problems like that before, you might start recognizing something called the IMODE correspondence. So these sort of Schrödinger operators appear in the context of integrability. And where do they appear? They appear in the study of Kondo problems. So what is a Kondo problem? Actually, before I go into physics, right, there are a few more questions. The question from Samson, I think probably yes, that you can write down a Yang-Yang functional for these beta equations. And I assume the derivatives with respect to the Z's and W's will give these parameters, but I have not checked. So one should check. The way you go from the, sorry, the way you go from the beta equations to the upper is very similar to the way to what happens in the standard Godin model. If you remember, in the standard Godin model, the way you get beta equations is by looking at Miura operas, meaning essentially you look at operas which can be mapped to a flat connection of a certain triangular form. Essentially, that means that this expression here, this potential here, is written has a form like v squared plus del v, where v is some rational function, and then finding that rational function gives the beta equations. If you look at this affine upper problem, essentially everything which is a quantum correction is a Miura upper. And you're trying to find this Miura upper in such a way that there is a trivial monodromy. Or you can, well, okay, there is a whole story about affine operas and affine Miura operas that Benoit has looked at. And they've been learning from him how to deal with this. But it's, you can write a couple pages long proof that this opera has trivial monodromy as long as the beta equations are satisfied. It's not complicated. Any more questions? So, right, so this equation has Stokes parameters at infinity. And actually, so you can, if you turn off these constants here, you set one of them to 0, you can remove this exponential here and just have a polynomial potential. I should have put a C here, I forgot. So you have Stokes data at infinity, a bunch of Stokes matrices. So there's a question from Samson. Yeah, I agree. That's right. If you go all the way to the gauge theory, you have your twisted effect superpotential, which becomes a Youngian functional. I've just not checked in detail the derivatives of the gradient of the Youngian functional gives you the Ci and di. It's probably true. Yes. Okay. Seems like I have still 12. Sorry, do I have 60 minutes or 50 minutes? 60. I forget. Okay, good. So let me try to do a bit more physics now. Kondo problem, the grandfather of renormalization. So the Kondo problem is, well, I guess the original incarnation was a single impurity interacting with a band of electrons. But if you distill the problem and simplify it a bit, you end up with an impurity in a two-dimensional chiral CFT. And the Kondo problem is about understanding the G flow of impurities coupled to a two-dimensional chiral CFT. The classical example is a two-level system, a qubit, coupled to two complex chiral fermions in a way that preserves a global SU2 invariance. So you take Pauli matrices acting on your qubit, and you contract it with Kac-Moody currents built out of the fermions. There is a coupling. This coupling is naive, classically marginal, but has an interesting RG flow. If the coupling is positive, marginally relevant, and so you have a nice UV complete line defect depending on some dimensionally transmuted scale mu, which you could write as e to the theta, or perhaps as 1 over h bar if you're making comparisons with previous slides. Now, there is some, so you start with a weakly coupled defect in the UV, you turn on this coupling, there is some complicated RG flow, and at some point strong coupling happens, and you end up with something completely different, which is a topological line defect across which the fermions are reflected. So, right, so if you stare at this interaction, right, if you replace this psi dagger with some J's, this is nothing else but this transfer matrix for a single site, I have a single copy of the Kac-Moody occurrence, I contract with its auxiliary polymatrices, I take it apart order exponential. So in a sense, right, defining this transfer matrices better be a rich problem, because even in the simplest situation of a single site for SL2, I encounter the Kondo problem. So there is definitely an interesting renormalization going on here, in the very least. It's interesting because the coupling ends up being closely related to the spectral parameter here. Okay, there are some nice fun details about the physics of these systems. Because of the chiral, because the bulk is a chiral quantum field theory, sorry. Because the bulk is a chiral CFT, where all the modes are, say, left moving, no degrees of freedom can bounce off your defect. So these defects are reflectionless, which means that you can move their position freely and rigidly without changing anything. But they are not topological. If you had conformally invariant defects in a chiral CFT, they would be topological. But if their defects break scale invariance, they also break, they're also not topological, but they're almost topological. You can add wiggles to your defect without changing the answer, as long as you make the local scale position dependent. There's a kind of a framing anomaly. And in general, it's useful to complexify this local scale and studying the defects as a function of this complexified scale, which costs you unitarity but gains you a lot of fun. You can have interesting phase transitions as you vary the imaginary part of this scale. The most basic observable you can compute when you have an impurity is the free energy of the impurity, the thermal free energy. Meaning you put your theory on a thermal circle, you wrap your defect along the thermal circle, and you see what comes out. Or if you wick rotate, you get a transfer matrix acting on the space of states on the circle. And again, this transfer matrix should be the main object of study in affine Godin. And it commutes with Hamiltonian because you can rigidly translate the defect. And you can compute it in perturbation theory. And when you compute it, you find something that, if you don't know about affine Godin, is rather surprising, which is these transfer matrices commute at different values of the local scale. So you have this family of line defects, which can be rigidly moved. It's parameterized by the scale theta, but surprisingly, the defects for different values of theta commute across each other. And the RG flow scale really plays the role of a spectral parameter. Sorry, go forward. And the affine Godin model immediately tells you that you should look at these Kondo lines for multiple copies of your Kac-Moody algebra and study line defects which couple to multiple copies of a Kac-Moody. These will be sort of multi-channel Kondo problems. And you get a prediction that you should have commuting Hamiltonians for any number of these Kac-Moody currents. But as I said, a lot of the studying this from the point of view of the affine Godin model is a bit tricky. But luckily, there's another nice perspective that helps explain all of this integrability, which involves four-dimensional Chern-Simons theory. And I will not even try to describe it now, but there's a beautiful story that Kevin has developed where you couple surface defects to four-dimensional Chern-Simons theory. And you can use these surface defects and the Wilson lines to engineer these Kondo problems and predict that there will be integrability, Hirota relations, and a lot of nice features. Now, I see some question again. I need to remember the reference for multiplicative geometric Langlands, but is multiplicative geometric Langlands what's called sometimes Q geometric Langlands? or is it something different? Yes, that's right. So Geometric Langlands has to do with looking at XXY or XXX instead of Godin. I don't think it's a generalization in the same direction. Sorry, answer is no, or answer is yes, Samson. Okay, yes. A reference for this commutativity. Well, so I think this was tested in a paper by sorry, I'm blanking out on the precise reference. In the paper I wrote with Jingxian and Jihon, we did a calculation up to order g to the fourth and checked, but I think up to order g cubed it was checked before, and we had the reference there. We also checked it for the multi-channel setup. Something very nice is that the four-dimensional Simons theory construction gives a prediction of what the beta function should be for these Kondo problems. And although the beta function for a single Kac-Moody is mostly scheme dependent, the beta function with multiple couplings has a lot of data which is not scheme dependent and gets predicted by as whenever we checked, it agreed with the four-dimensional Simons predictions. Right. Now, the interesting thing is that these integrable Kondo problems, I've been studying it in the integrability literature for a while. There is a whole story about T equations, thermodynamic beta stats equations. There's this IMOD correspondence, which predicts that the transfer matrices should transport coefficients of some opera. And now this is precisely the sort of operas which we encounter by looking at affine Godin models. So in particular, we can get a full answer for the IMOD correspondence for all the excited states of the Kac-Moody currents. So, right. So typically in the IMOD correspondence, one writes down equations which give you the transfer matrices for the acting on the vacuum of your WCW problem, of your chiral fermions or whatever. So sorry, that's the wrong button. So the IMOD correspondence typically gives you the action of these transfer matrices in the vacuum, and then with some extra work, you can sometimes figure out how to put excited states in the story. And this affine Godin model and this perspective gives you a very precise way to get these excited states by solving these beta equations. So you find beta equations for these integrable Kondo problems. Okay, I'm sorry. So I've dragged you through a very long and meandering set of problems. I'm sorry for that, but it just I wanted to give you the impression that there is a lot of interesting problems and interesting results which seem to be partly uncovered, which have to do with the affine geometric Langlands program, with the quantum toroidal algebras, and with the IMOD correspondence. And we're trying to uncover some of these connections, but there is definitely a lot of work to do. Okay.
Thank you very much. Yeah, thanks, Davide. Are there a few questions that the audience would like to ask?
Can I ask a question? This is Samson.
Yes.
You can do two things, right? One thing, go from 4 to 5 and 6 dimension on the circles, or instead of quiver, you put affine quiver. So you can do two different things, or you can do both.
Yes.
So my comment is that there was a question how it relates to the relativistic kitchen system, or what multiplicative. And my understanding is that what you are discussing is you are taking affine quiver. What they were discussing were 5-dimensional gauge theories on a circle.
Yes.
Which is, I mean, you can do both. And in some paper I wrote with Vasily Beston and Nikita Nekrasov, we wrote Baxter equations for general situation when you add the circle and consider affine quiver. So you are taking one of the limits, and question was about another one. Am I right?
Yeah. So I'm definitely interested in the 3-dimensional theory for the affine quivers too. But yes, for this particular connection to affine geometric Langlands, I would go down to the affine Godin model.
Right. And there also, David, there was another comment. I'm sorry, I take a time. We had discovered that if you take a Baxter equation for XX spin chain and do some Fourier transform, you get the Baxter equation for the Godin.
Yes.
And this
trigonometric Godin.
Yes, yes. I mean, the statement is XXZ and whatever. Yeah.
Yes.
This has to have implications on what you are doing here, I believe, right?
Yeah. Let me say something about that. Let me put a new slide. Okay. So we have suppose you take your 3-dimensional theories. Now, there's some compactified on a circle. There are some mass parameters and some Fi parameters, and they give you the XXY spin chain, right? Then this is self-mirror. So you can apply your 3-dimensional Gaussian theory. So you can apply mirror symmetry to it, and you get sort of two different set of Bethe equations, two different spin chains which are associated to the same theory. And the mirror symmetry exchanges Fi parameters and mass parameters.
Yes, I agree. Thanks.
Now, if you take a sort of a naive scaling limit, you can go from 3D to 2D gauge theory. If you look at how this scaling limit behaves, though, it treats the 5 parameters and the masses in a sort of asymmetric way. As a result, you really had two different 2D limits, which are exchanged by mirror symmetry, by the 3-dimensional mirror symmetry. So one of the two limits will give you XXX. The other will give you trigonometric Godin, and 3D mirror symmetry will permute them. Alternatively, you can get a sort of a symmetric scaling limit, which treats Fi parameters and masses in the same way. This does not give you a gauge theory. This gives you something, it's a limit of a gauge theory. I think it has to do with the volume theory of M2 branes ending on M5 branes, as I was mentioning. But this one treats masses and Fi parameters in a symmetric way. So it gives you the rational Godin model in two different ways. So, so in 3D, there is a XXY mapped to itself by bispectral duality. A level down, there is XXX versus trigonometric Godin related by bispectral duality. And then all the way down, you get just rational Godin, which is again self-dual. The same picture you could draw for the affine case. There is a quantum toroidal spin chain, which is known to have bispectral duality. You can take a scaling limit to a Youngian based spin chain or to an XXX spin chain, affine Youngian or XXX, and I assume they will be related by bispectral duality. or you can go all the way down to the Godin model, to the affine Godin model based on the Kac-Moody algebra, which will be self-dual under this bispectral duality. I hope this answers the question.
So there are a few raised hands, but there are also a few more questions left in the chat.
That's right. So the next question from Sasha, from Jasha.
Yeah, so there's a question from Yasha right at the end of your talk about varying. And,
that's right. Excellent. So I had a picture here. So this is what happens to the basic Kondo defect as you vary the scale. So to the very left, there is the defect defining the UV with a positive coupling. And then you float to the right. If you turn a large enough imaginary part, so that the defect is quite not unitary, you get one of those funny G-flows that go back to the starting point. So you loop around the space of coupling, so you come back from behind. So you end up with the negative value of the coupling, which gives you an infrared free defect. You do the same with large negative imaginary part, and you go back again to the infrared version of the Kondo defect. On the other hand, if the imaginary part is sufficiently small, you go to this strongly coupled RG flow down to topological defect. At the transition, what happens is that there is a level crossing, basically. You know, the eigenvalues of your problem are imaginary, are complex now because there is no unitarity. And you can have true eigenvalues which whose real part crosses each other, while the imaginary parts are different. And when that happens, sort of you get a phase transition. You change your dominant ground state. And so, yeah, it's kind of a screening transition.
Do you want to take the question from Sasha, and then we'll take John Harnett?
So, well, the basic statement would be that affine operas, that affine operas are in one correspondence to solutions of the to states in the affine Godin model. So this should be analogous to the relation between standard operas and standard Godin model.
What happens to replacing the group by its dual? What happens to? I mean, usually you have to replace the group by its Langlands dual. So what?
Oh yeah, here too. I think here too. Although I don't know exactly how the Langlands duality works for affine algebras, but
it makes sense.
Yes, so I expect something like that to happen here too.
And then John, do you want to unmute yourself to ask?
Just very quickly. So earlier you mentioned, I guess it was work by Kevin, which related to other aspects of integrability, and you mentioned the Hirota equations. Could you just comment on the relation between the Hirota equations and the beta ansatz?
So in the four-dimensional Chern-Simons setup, there are Wilson lines which, due to some quantum corrections, have to carry representations of the Youngian of the gauge algebra instead of being representations of the naive representation of the gauge algebra. And when you fuse these Wilson lines together, they fuse the same way as representations of the Youngian do. So the Wilson lines naively are parameterized by the position in some complex plane. But when they fuse, sorry, I have not written it down, but anyway, this position plays the role of a spectral parameter for this Youngian representation.
Could you go back to that slide with the bilinear relations?
Yes, here. That's right.
So can you just, that's the transfer matrix.
That's right.
These are functions or they are operators?
These are expectation values of transfer matrices on on some eigenstates.
But so this is not usual Hirota. You would have another pair of terms somehow, I mean quadratic terms in the usual Hirota.
No, this is still true. This is still true Hirota.
But you have linear terms and quadratic terms?
Well, it's because, right, if you write Hirota for GLN, there are terms where you shift, how can I say this? I think this is the Hirota for SL2, right?
Hirota is usually bilinear.
Yeah, but the part of these bilinears involve the determinant representation of SL2, which is just trivial.
Mm-hmm.
Sorry, Davide, once you identify Baxter equation, so once you know what is the Q of Baxter equation corresponds in gauge theory,
Mm-hmm.
step to Hirota is direct. It's the same way as you do always.
Yes. So
and
here,
we know what is Q in gauge theory. I mean Baxter Q in gauge theory. Once we know that, we are done.
well, that's okay, right? So that's for the non-affine case. In the affine case,
affine also. Sorry,
it's
affine
more
also.
complicated.
No, affine also.
See, it's not quite as easy. So,
well, Baxter operator basically is the same as an operator. So you had the operator; it has a meaning. Anyway, I believe that there are formulas for the Q, nice ones that lead to this.
So what I can say is that the T defined. So I keep going in the wrong direction. The T defined by this sort of Lax matrix satisfy Hirota is related to some Q, but that Q is not is not a polynomial whose roots are these W's.
No, that's the result. Sorry. That's a result of the beta. You have to satisfy beta equations, then you get this.
Yeah, but I'm saying that I don't think these beta equations arise that way. I might be wrong. I need to double check. But very roughly, Q, the role of Q is played by the wave function.
Yes.
By this wave function in the Schrödinger equations.
And we know what psi is in gauge theory, right?
So what's going on is that in the usual case, once you know your Miura operator, psi is very easy to find. So essentially, the Miura operator is an operator where psi is a rational function, pretty much, which is Q over some polynomial. Okay, but here it's not as easy because now there is an actual potential in the Schrödinger operator. If you send h bar to infinity, then psi will become a rational function, but not for generic value of h bar. For generic value of h bar is a very complicated expression. It's not like it's just not known. And right, anyway, the short answer is that I do not know of an easy way to relate the beta equations to some TQ relations. There are TQ relations here, there are beta equations, but I don't get one from the other in this setup. It might be possible, or you might have to look at some other set of T functions and Q functions. So as far as I know, there is something different happening here, but I might be wrong. I still have to, I'm happy to change my answer if somebody figures out. Now, going back to the Hirota.
There was also a comment at the end of the chat asking whether there was a typo in.
No, I don't think there is a typo. The Hirota is a deformation of the relation that holds for SU2 representations, right? If I take, maybe there's a typo. Yeah, sorry, you're right. There is, of course, a typo. Yeah, it was 1 plus product of these. Yes. Yes, sorry. That's right. I was thinking about another Hirota relation when I was writing this, where there is T2 times T with different shifts. That's right. Okay.
Sum is a product?
It was 1
sum
plus the
of the group of-
product, yes.
Ah, that makes it bilinear. Okay, great. Well,
Yes.
there's still the one.
As the comment explains, that's correct. And so, right, and here it's fun, right? So this theta is this complexified scale. So even to write this errata, you need to move away from unitarity.
There were a few more questions in the chat and hands. There's
Going
a
back.
word.
So I asked if you
Yes.
could just repeat the relationship of that path ordered product you had to the Kondo problem.
Yes, that's right. So the Kondo problem, sorry. Okay, it corresponds to turning on some interaction, right? Which couples a WCW model or a product of WCW models to an impurity. So if you had multiple WCW models, you would just take some linear combination of the currents, depending on some GIs, and contract it with some polymatrices acting on the impurity. And that's precisely the form of the transfer matrix for the fine-Godin model. You take a bunch of Kac-Moody currents, depending on the coordinate W as usual. You contract it with some polymatrices, and you do the Patogov exponential.
What does the 1 over z minus zi mean in the
So this is just a particular parametrization of the couplings.
Oh.
So this was just standing for some GIs, if you want.
Oh, I see. Sorry. So I should think of that as a coupling constant, and T are
Yes.
the group generators acting on the impurity.
Yes, that's right.
So this whole thing is a matrix that acts in the Kac-Moody representation, tensored with the Hilbert space of the impurity.
Yes, that's right.
Okay, thanks.
And so when the z minus zi's become large, then the system is weakly coupled. And this parameter z is roughly theta. It's related to the scale. More precisely, you can write down some.
But this needs, the Kondo problem needs so much renormalization that I'm surprised the classical expression you wrote means anything. Could we go back to it again and discuss?
Yes. Well, the renormalization is not too bad, right? You only need to consider operators of dimension 0 and 1. So there is an overall rescaling from the operator of dimension 0 from the identity. And then the coupling gets normalized.
Yes.
So
that means
sort of hide it in
take
alpha.
the function alpha over z minus zi. We can't take that literally. That's a classical formula, but
Yeah, you could say that there is an alpha z, zi, and theta. Theta is the scale.
I see. Okay.
And of course, there is a certain degree of arbitrariness in writing down beta functions, but from four-dimensional Chern-Simons theory, you get sort of a perspective where the z, which I wrote zw as w here, has a beta function, and these i's can be kept fixed.
And how literally were you talking about a framing anomaly? Can you help us understand that a little bit?
So in the four-dimensional Chern-Simons theory, there is a framing anomaly.
Yes,
where
that one I know about. Yes.
That's right, the one
everybody. Yes, go ahead.
You wrote, where if you translate in the topological, if you rescale the topological direction, you need to pay the price of a translation in the holomorphic direction. This translation is a translation.
Also, sorry, excuse me for not speaking. In that case, if you bend in the topological direction, you translate in the holomorphic direction.
That's correct.
If I recall properly.
That's correct. And this translation is in a local coordinate where the action is just the theta, the z wedge Chern-Simons.
Yes.
In this setup where there are surface defects, you need to modify the action a little bit by putting an interesting one form. And so this shift will, when you had to define sort of a local coordinate theta, and the shift will shift theta. Anyway, this is a small detail. In the case of the Kondo problems, yes. So you can try to bend your defect by applying a conformal transformation. This conformal transformation will leave, will leave the bulk unchanged, but it will actually act on the defect in a non-trivial way because the defect is not scale invariant. And if you keep track of what's happening in terms of the defect, you find that as you change the shape of the defect, you also shift the local scale by a certain imaginary amount.
You're thinking of this in Euclidean or Lorentz signature for the Kondo problem?
Euclidean.
Okay.
Yes.
The setup, of course, makes sense in Lorentz signature, and you could have an arbitrarily wiggly defect. And then
I think in Lorentzian, it would be really a real shift of theta. So if you boosted the defect, you would have a real shift of theta. And this theta behave in many ways like a rapidity.
Okay. Thanks.
And if you match the parameters, so you match this little omega I was mentioning, the framing anomaly on the Kondo problem takes exactly the same form as the framing anomaly in the Fordich-Simons theory.
So maybe we'll take one more question officially, and then we can keep discussing as long as Davide is willing to.
Yes.
You've had your hand raised for a while, if you're still around.
So there is still a question in the comments. What can be said about the space of affine operas? Which should I answer first? Sorry.
It's
Okay.
there are a few lying around. I was going to actually call in Sherry.
I'm here if you want me.
Yeah, please.
Thanks. Well, it's actually related to the last question in the comment somewhat and to Greg's question. So trying to think of affine operas in terms of either Higgs bundles or flat complex connections. So the classical opera can be thought of as a filtered bundle with the connection, and the connection satisfies this Griffith transversality and some other properties. Is there any way of thinking of these affine operas in terms of certain special vector bundles or flat connections? For example, does this psi x, is this a flat section of some connection on your space?
Yes, I mean, so there are sort of two different perspectives. One is that you really work for operas for the affine group for Kac-Moody. But leave that aside. Here, when you're really looking at standard Schrödinger operators or operas, the crucial point is that there is an h-bar parameter. So it's really an h-bar opera. It's like a lambda opera. It's a one parameter family of operas.
Right, I see. Okay. So it's these lambda connections and lambda.
You want the trivial monodromy to be true for all values of h-bar.
I see. Okay.
So I can imagine something like that happening in a Hitchin system too.
Right.
Where I add a regular singularity, adjust the parameters so that the monodromy eigenvalues are trivial, and then require the monodromy to be actually trivial for all values of the spectral parameter. I should also say that there is a whole interesting story about the IMOD correspondence for Hitchin systems. Right?
Nice.
If you wanted to study, what's named? Right. So here we had defects. Right. We had a chiral fermions, and we turned on a defect. Now there is of course a much more interesting problem where you take chiral fermions and deform the bulk theory to get a chiral. So what's the name of the model? You get Thierry model. Sorry. Not the Thierry model. The one where you add a bilinear of currents. So suppose you have non-chiral fermions now, both holomorphic and antilomorphic fermions. And now you can add something like JG bar to your action. Right? You get an integrable system, which has a very nice solution in terms of TBA equations for computing the vacuum energy, say. And then you can try to figure out what are the excited states of this system. And there is an IMOD correspondence for the vacuum that is based on the Hitchin system. Hitching system with similar shape as the shown equation. I can hope that the excited states for the system will involve a Hitching system with extra singularities, so trivial monodromy. But I don't think this has been worked out.
With this thing, okay. That sounds interesting. And there's a small question about affine Godin. Is there a representation of braid groups related to affine Godin somehow? Because this transfer matrix or this path order thing seems like basically a representation of a generator of an element in the braid group. So if you go back to it, actually, you didn't tell us what you're integrating over. That's a path in...
Sorry, right. So this is a Kac-Moody, these are Kac-Moody currents. I collect them together as an element of the loop. Right, so this W is a loop parameter. And this total exponential is around this W.
I see. Is there a geometric interpretation of this loop around W? What is it?
Not sure. I mean, in the quantum field theory setup where these are Kac-Moody currents, this is a natural way to define a line defect. But
this thing.
Mathematically, I'm not sure. And I'm definitely curious about what do we do with the braid group representations if I start braiding around the Z's.
Right.
Now, notice that
thinking. That's the...
it's a bit subtle because, well, okay, yeah, I can braid the Z's. I don't see why not. And I'm not quite sure what the meaning of that is. I'm quite curious. When we're studying the finite Godin model with Edward, we interpreted these beta equations, which now disappeared. So we interpreted beta equations as saddle point conditions for some integrals, which are the free field realizations of conformal blocks.
Right.
It's like something to do from classical to quantum geometric Langlands.
I see.
I could try to interpret these affine beta equations as saddle pointing conditions for some integrals, but I have no idea which kind of conformal blocks these integrals will produce. I couldn't figure it out.
Since it's gotten a bit over time, we should all thank Davide again. Thanks for the fantastic talk, officially. And then as long as if you're willing to hang around and keep taking questions and discussing, we can do that.
Yes.
But yeah, thank you.
So I mean, there is a braid group representation, in fact, a mapping class group representation associated with the quantum groups.
Mm-hmm.
Right? Or in particular, quantum groups at roots of unity, those give you finite dimensional representation.
Mm-hmm.
So, I mean, if these things are generalization of those, then they should contain finite dimensional representations of a mapping class group as well, or braid groups at least. That's the...
Yeah, so it should have something to do with affine quantum groups.
Right, that's true. So they might not be finite dimensional.
That's right. So if you look at solutions of these beta equations, they build up Weil modules rather than finite dimensional modules.
I see.
So it's fun to see that if you start solving these equations, you find the correct number of states at each level, and to match the Weil modules of Kac-Moody with specific levels and spins. As you vary the spin, you see that some beta roots disappear whenever some null state appear, and things like that.
I see. What is the level of the in the Kac-Moody picture correspond to? And
so here the levels are the sum of these k plus k primes.
Right. Okay.
And the spins are just the k's.
Mm-hmm.
And spectral flow exchanges k and k primes.
Cool. Okay, so that maintains that. And do you expect any kind of rank level duality of CFT here?
I think so. There should be definitely a bispectral duality here, inherited from the 3D mirror symmetry of the 3D gauge theories.
On this page, probably there is typo in the first line on this trace of P exponent. W integral, there is integral of W and W enters only in current.
Yeah, that's right. That's
so
not
this
right.
alpha Z, Zi doesn't depend on W.
No, these are just, alpha is just a normalization factor, and Zi's are the impurity parameters of the.
So it's like in universal enveloping algebra, you just take normal P exponent, but you weight differently J's depending on this alpha.
Yeah, that's right. See, right.
See, there is another formula which says that suppose you have this trace of P exponent, like in conformal field theory, where all these alphas and z's are absent, you have just trace of integral of current, right, which is a group element. There is a statement that if you put some kernel in this integral, dw, jw times some kernel, which depends on w and z, you see, when alpha depends on w, then there is a claim that that particular operator that you get, it will not be vertex operator in the Sumina-Witten model anymore. It will be something called Fadeev-Zamolodchikov algebra for integrable systems, which has also quadratic exchange relation, but with R matrix, which depends on spectral parameter. So basically, if you take P exponent of some kernel times a current, an integral, depending on the kernel, this is always some element in universal enveloping algebra, right?
Yes.
So if you pick that kernel to be just a step function or something constant, then you get the vertex operator in the Sumina-Witten model.
Okay.
If you take that kernel to be something else, like trigonometric or elliptic or something, you get some operator. You can again calculate exchange relations of those operators. And with the correct choice of these alphas, the kernels, you can get exchange relation, which are called Fadeev-Zamolodchikov algebras, which is same as in CFT, but R matrix depends on spectral parameter.
So in this setup, right, I don't know how, there
has to be, what I'm saying, there has to be an exchange relation for these operators, which has some meaning in this integrable system.
So the four-dimensional Chern-Simons theory construction implies that there should be some kind of R matrices for these Kondo defects, where you have two Kondo defects which intersect each other, and you put a very specific R matrix operator to the vertex.
I think that it is known by now that this four-dimensional Chern-Simons interpretation is kind of dual to my work with Nekrasov, beta gauge correspondence. So these two things are in string theory setup dual.
I would, as I stressed at the very beginning of the talk.
Oh, I missed first 15 minutes. I'm sorry.
Okay, so
I missed. Sorry, I apologize.
A relation between the XXX or XXY beta gauge and for Chern-Simons, but that's not the relation which is appearing here. It's a different duality chain. It's a different.
So, but at the end, it still ends up to be a beta gauge correspondence. All the rest of the equations were, I'm sorry, recognizable for me.
There is no, it's not a good analogy.
It's not? But it would be good to see what the exchange relations for this P exponents.
Yeah, so writing down these R matrix operators is a little tricky because, already renormalizing the line defects was a pain, and renormalizing local operators at the intersection of two renormalized defects requires a lot of.
In some limit, I mean, classically, just think about this classically. J's are just have some Poisson brackets with Kac-Moody.
No, okay, if you do that,
it's already interesting.
You have some difficulties working with this non-ultralocal.
No, sorry, Davide, I meant that if you do it classically, so J's are have some Poisson structure. You have this formula, compute Poisson bracket of these.
No, absolutely.
If you get classical, So if you get classical R matrix, you are done. Then
yeah, that's right. That's what Benoit and others have been doing. If you study the classical limit of this,
I'm sure it's some classical
matrices, you get local Hamiltonians. The quantization is tricky.
Well, according to Driffield, once you get a classical R matrix, quantization will replace it by quantum. There is some general hardcore mathematics that Drinfeld developed that classical R matrix gets quantized and becomes quantum.
Problem is that it's not a matrix; it's a local operator on a non-trivial line defect.
Yeah.
So the point is, this is not a lax matrix. Once you go to the quantum problem, it's not a part order exponential of a lax matrix. It's a line defect defined by turning on an interaction and doing an RG flow. And whenever these line defects intersect, where you have local operators on these line defects, they need to be, when you know that defining local operators in quantum field theory requires care and work, right? You need to renormalize them, regularize them, and all of that. This means this makes a lot of the standard manipulations a little bit suspicious until you make sure that renormalization does not ruin them. The Fordician-Simons theory setup is beautiful because, at least in perturbation theory, it guarantees that all these manipulations will work.
Except
the Feynman diagrams of the Fordician-Simons theory automatically produce their matrix and all the quantum R matrix and all of that.
Yeah, except it's not gauge invariant, right? For large gauge transformations. For elliptic case.
Right, I was not looking at the elliptic case here. But also it has another problem that could bother you, which is not non-perturbative.
Yeah, it's not, yeah. But your story, I'm sorry if I'm asking too many questions, but I'm interested in the subject. So your story basically can be told straight from the beta gauge correspondence.
That's what I tried to do in this talk, yes.
Right, without any reference to that. So in order not to get
confused. At some point you get here, right? At some point you get here and you need to do quantum field theory. So to make sense of this matrix, you need to think about Kondo problems.
Yes, so question would be, if you are straight in the language of beta gauge correspondence, you have to say what this operator is. Even axiomatically would be good.
Right. Although, as I mentioned, I find it interesting that if you do not go to the Gödel model, if you stay up in the quantum toroidal algebra setup, I suspect that this renormalization issue will not occur. Perhaps there will be other renormalization.
Are you saying that in quantum toroidal algebra language, this will not be some kind of vertex operators there? There is a notion there of that also.
No, there is going to be. This is just a transfer matrix, right? It's a product of our matrices. You take an auxiliary representation, you cross all your spin chains.
Yeah, I understand. It's total product, yeah.
Yep. So you do that with the matrix of the quantum toroidal algebra with appropriate representations, you get the transfer matrices.
Yeah.
Now that our matrix is a formal sum, so perhaps a renormalization will come out there. Right, these are matrices are always written as some infinite sum of things. But I don't know enough about the details to know if there is an analog to the renormalization issues.
So what is TQ equation here? Is that something simple we can look
at? So these transfer matrices satisfy a TQ relation where Q is literally the wave function.
Yes. So we know what is the meaning of psi in gauge theory, right?
No.
We don't know?
No. So one of the things that I've been trying to make sense of, and it's still a bit escaping me, is how to get a good, clear meaning for this psi. I have some ideas, but not quite precise enough at the moment.
I would return to the beta equations and the QQ systems, and operas. So there is a way to understand how the beta equations for the quantum, for the ADHM quiver, say for the necklace quiver, they arise from the A-type quiver for a large number of nodes. So you need to make certain identification of Coulomb parameters and make some change of variables, so you can rewrite the beta equations for the long quiver as a beta equations for the ADHM quiver. And then when you do the identification of Coulomb branch parameters, you get the third parameter, which then will translate into the parameter Q3 in quantum toroidal algebra. So if you're in terms of physics, it's certain, you can think of it as a choice of the quantization condition in the Gilbert-Kummer-Waffe formula. So there's a kind of, on the left, we have a result situation, and we have many D3 branes that wrap the S3, right? And then there's a resolved side where you get a resolved conifold, and then sort of if you reduce the 11D supergravity on the resolved conifold, you get the 5D Young-Mills, and then the ADHM quiver will count instantons in the 5D Young-Mills theory. So there's a physics description of that, but in terms of sort of mathematically, it's a very well-defined procedure. So there's a way to get to this beta equations for the HM quiver from A infinity or gel infinity quiver, and the same can be done for operas. So in other words, you can get the quantum toroidal opera from gel infinity opera. So we believe we can do that. So now, when you say that your affine opera is the same as, you can understand it as the regular opera, but with some extra data, you say something different. But can you think you can interpret this additional corrections in the potential as sort of in terms of what I said, sort of this?
It's not very clear to me how you're going to get an non-trivial potential starting from an opera of trivial monodromy, even sending the number of singularities to infinity.
Well, I mean, you'll capture some sector, right? So in ADHM, you have some fixed instanton sector, and that would correspond to certain number of branes like there.
Yeah, sorry, I don't think I can reconstruct the details well enough to answer your question here.
But what's the meaning of, is there connections? How H bar is related to Q3 or to other?
No, so here we turned off Q3. So it's important that, sorry, go back. Yes, so when we went from the quantum toroidal case to the Feingold case, I also turned off this bifundamental mass.
You take this double scaling limit when it disappears, okay.
Well, before even doing double scaling limit, I turned off this extra mass, which means that the quantum toroidal algebra becomes the quantum affine.
Okay.
The affine quantum group, I think.
Yeah.
Well, yeah, I guess I'm thinking about the full case,
right.
quantum
case. When you do that, the sort of the GL1 factor in GLN goes away.
Mm-hmm.
So if I try to do the same thing to the ADHM quiver, you get nothing literally. The beta equations just go away. But if you do it for the 2-node quiver, you get an interesting SL2 affine problem.
Mm-hmm. Yes, that's enough.
Can I get permission from the chair for one more question, maybe?
I think at this point, we keep going until the audience exhausts itself. So.
Okay, so in that case, Davide, think about this in terms of some your correspondence with Aldai and Tachikawa. Is not it a classical limit again of something there? So there is a conformal block now becomes whatever something, and this story should be classical limit of it. So what is the meaning?
There is something here that
What is the meaning of, in that case, now psi gets promoted to conformal block, right?
Right, so there is a piece of the connection that I'm missing, but
so in terms of AGT,
right. So it's definitely true that people have thought about AGT using affine Youngians. And
yes, that we know. Now we are taking some double scaling limit. So we have AGT there. Then we take some, we go to the beta gauge correspondence by taking some double scaling limit. So we know the meaning of psi in the gauge theory. It's like, Pestun and Nekrasov.
It's not clear to me that you get a spin chain for the quantum toroidal algebra in AGT.
Okay. So you are saying that you can do this manipulation, but you don't know how it is related to the spin chain picture.
So what I'm saying is that the sort of modules which people put at individual sites of the spin chain arise also in AGT.
Right, but what I'm saying, we forget for a spin chain for a moment. So spin chain will come to the picture related to quivers, right? What quiver we do that way. So let's forget that it describes a spin chain and just think about the gauge theory language, right? So you have AGT now for these quantum toroidal algebras. You take the limit when it becomes beta gauge correspondence, right? Yes. And now if you knew the meaning before taking the limit, it becomes, from the gauge theory point of view, just a limit. But from explaining in terms of beta gauge correspondence, it becomes the transfer matrix or something like that. So all these operators we can describe as the limits in the gauge theory. Just example to bring the Vasily, Nikita, and I wrote how to think about Baxter operator divided by shifted Baxter operator in terms of determinant in the gauge theory, determinant of some whatever, if you know, x minus phi or something. So there is a notion of y as q of x plus 1 divided by q of x in the terms of gauge theory. And then we know that this particular y will satisfy equation which is called Baxter equation, but in this language it becomes statement that the character as defined, quantum character as defined by Rishtichin and Frankel is equal to transfer matrix. So on the left-hand side, you have quantum character, which is defined by your affine quiver, right? On the right-hand side, you have some whatever transfer matrix, which is not always polynomial, but it's equal to polynomial. So we know the meaning of the left-hand side of operators in Baxter equation in this theory in terms of gauge theory.
Yeah, but I think at this point you're accumulating too many things that are being called transfer matrix.
Or call it something which is polynomial. So you get quantum character equals polynomial.
Mm-hmm.
That kind of equation.
I don't think what you're discussing is related to the transfer matrix and Q functions of the quantum toroidal spin chain.
I think that spin chain will be defined by what I put in a quiver, and in cases I know it is true. But what I'm saying is that there is probably a way to explain this in terms of AGT. I just propose some way in which I know works in cases.
I'm not sure.
You're not sure?
Some of the things that confuse me is that I know now many different ways, multiple ways to get to quantum toroidal algebra, for example, from gauge theories. And they don't seem to be equivalent. They're related by some bizarre dualities, probably. For example,
in a sense, you get AGT, but sort of in a different frame, right? Like you know, you get say to get to the quantum toroidal algebra, you get AGT for U1, right? You have this JL1 hat algebra.
So, for example, in the gauge beta correspondence, the quantization parameter is this n equal to star mass deformation. In other constructions, the quantization parameter is an omega deformation parameter.
But they're related by some Fourier transform.
Yeah, yes, no, absolutely. If you do enough dualities, you can relate them. But
well, of course, what I was saying, Davide, was in terms of the omega deformation in that language. But you can keep there this mass parameter. I mean, there is no problem. You can take the limit, don't take the limit. Anyway, it would be interesting, actually, if all this can be unified. Well, one thing that unifies it is a beta. I mean, one thing certainly unifies it is beta gauge correspondence, but there are too many things that are happening that look similar and not always the same. So
yeah, that's right. So the quantum toroidal algebra can appear in different roles. The Youngians can appear in different roles, pretty much because, you know, whenever you have a 5 brane, you can find the Youngian somewhere.
Yeah, what was for me also always puzzling, David, was the little string theory way of thinking about this.
Mm-hmm.
Because little string theory cannot be defined on anything. I mean, it is very sensitive as a decoupling limit
Yep. Yeah, we're curious to know if there is a four-dimensional little gauge theory. You know, I think of four super meals and but some UV complete. Well, something that in the infrared becomes an equal four super meals, but has extra particles.
Yeah, I've been thinking about
like massive Wilson lines and massive toothed lines.
Right. I think that the little string theory on T2 as a four-dimensional theory, of course, is a four-dimensional theory which is ultraviolet completed by little string theory.
Yeah, and I don't think it has a.
It doesn't have its own. Yeah, yeah.
but it still has a duality, and presumably is the setup for affine geometric Langlands.
Yes, yes. Thank you very much. Thank you very much.
Davide. And yeah, thanks, Samson, for all the questions. Also nice to see you again, virtually. Yeah, and thanks, Davide, and thanks everyone. Let's wrap this up today, and hope to see you all soon at some point.
Okay, thank you very much.